We have Benjamin Wolba. Currently, he's at Lunar Ventures, but he's also a physicist with expertise in quantum theoretical physics on condensed matter. Benjamin, floor is yours, please.
Lovely, thank you very much. Yeah, I'm Benjamin, physicist and with Lunar Ventures, so yet another venture capitalist in this session. Will be quite some overlap with what Ilham said, but generally looking into the current AI and semiconductor hardware stack. Since ChatGPT, everyone has realized AI is happening, and so now the application layer is extremely busy. And the main question is, what's happening beneath, on the various hardware layers? And that's not just chips. And that's what I want to address in this short keynote. So maybe to kick us off, how did we get here? So when we get back, a few decades, when the transistor was invented and people were doing the first chips, those were not super powerful. So they were application specific, and you would tailor these chips to what you would want to compute, which is probably also what you would want to do when you started in quantum computing, to design a chip for a special molecule or any other niche use case that this might become valuable for. But then something happened in compute. And that was the the central processing unit, the CPU. So you had a chip that was powerful enough to address various use cases, so it was just not economic anymore to do specialized chips. And so that was generally the era of Moore's law, where you had basically just one flavor of silicon chip, the CPU, that got just increasingly stronger every year. And you couldn't count at it, and you could literally say, okay, in a few years, we will be there, and we'll have this much processing power, and we will be doing amazing things with it. Think of Google offering tremendous amounts of storage capability to people just because they knew extrapolate Moore's law, and we'll get there. We'll make it economic to offer this to people. And then, what happened lately? We've been still seeing some increases in compute power, but about since 2006, those have not been coming just from the core, from the number of transistors, from one unit, but rather through parallelization, through adding more cores, by going to GPUs and basically doing multi-core compute. So in that sense, Moore's law is still alive. Like, we still see more powerful processors, but not in terms of the transistors. And this is just natural. You're hitting physical limits when your transistors really shrink down to the scale of nanometers. It just becomes incredibly hard to move electrons around. And so what to do about this? There are a couple of novel approaches, both to address these bottlenecks that come from physics, but also requirements that come from economics. And there's one major trend, and that is AI. And that is really to Oliver's thesis on software will shape what hardware we're going to be developing. So far, we could address all kinds of different use cases with a CPU. But now there's one use case that's sort of overwhelming, and that's AI. And AI needs just certain kinds of operations, really just matrix vector multiplication and a nonlinear activation function. But it's really a lot of linear algebra. So a very simple kind of operation, but that you need over and over again. And now it has really become worth it to explore avenues how to make that more efficient, to do all these matrix multiplications. And so there are different levels on how to think about this sort of unbundling of chips, of the CPU. You could do this on different levels. One is basically you stick with zeros and ones, you still do digital compute, but you start again to design more specialized chips, which could be application-specific integrated circuits, ASICs in short. That would be one approach to this that, for example, Google is taking with the TPU, or Apple is doing with the NPU, the neural processing unit. Those are ASICs. And they may be orders of magnitude more efficient, but it's still the same paradigm. It's digital compute. Then once you go one step further, you could even change the paradigm of how we do compute. Like, not necessarily 0 and 1s, but actually use analog hardware, like literally take the absolute physical value of a quantity to perform compute. And for example, if you talk to Annabret, these guys have been around this morning, they build analog computers. And they do analog compute to solve partial differential equations, for example. And you could do a similar thing to embody neural networks by hardware design. So you're not computing, zeros and ones and matrices, but you literally encode the activation function of a neuron by hardware design, and are thus much more efficient in your inference once you deploy such an AI chip, say on edge, NVIDIA camera to detect a cat that is running around or something more useful. So that's an entirely different paradigm, but it still sticks with silicon, with semiconductors that is sort of established. And then if you go one step further, and we've heard a lot about quantum computing today, we'll hear a bit more about optical computing. There are all sorts of new approaches to leverage different physics for compute. Like, no one says you need to use electrons and, zeros and ones, but really, what are the fundamental principles of physics that we can use for compute? And that's like a whole different category that might open up. And so we'll stick to the first two for this purposes, since we heard a lot about quantum already. Just to put those shortly into perspective, we come from one processor, CPU, that does sort of everything. And we know, depending on how general or how specific you go, you might have these ASICs or FPGAs that are sort of customized digital chips. You have neuromorphic chips also somewhere in here, and then you have GPUs, CPUs, and maybe, the potent quantum computer of the future that can do even things computers can't do today. So we'll focus a bit on everything that is on the left here on the AI hardware stack and semi-industry. And, since I'm a venture capitalist, my job is to find companies that can go as big as Apple or Google, or what's the next NVIDIA, right? So really thinking, what are the big opportunities to create a generational company in semiconductors? So here are a few ideas. Number one, it starts at the very bottom of the AI hardware stack. It's not actually hardware that goes into a chip, but it's the hardware to produce chips. And I pulled up this very futuristic image from DALI. This should be something like lithography. So lithography currently is the process of how you do chips. Like, you have deep ultraviolet lithography that is now being pushed into ultraviolet lithography, EUV. And there's a more or less near monopoly on that. That's ASML. And it's one of the best monopolies in the world, really, when you look at the financials. But the question is, what comes next? You can push EUV to a certain degree through, high-NA EUV and really push this to a certain range. But at some point, you'll be limited by the physics of just how much you can bend ultraviolet light. And the question is really, how do you get down to a transistor that, is just a few nanometers large? Not that large. How you get there? One approach might be to use atom-based, specifically helium atom-based lithography, where MIT people, but also TSMC and a couple of others have looked into this from a research perspective. The idea is to use atoms, which from quantum mechanics we know, they also have wave properties. And since they're matter, they have actually a lot shorter wavelength, which means they could resolve a lot smaller structures. And it might allow you to create transistors that are, just 10 atoms large, or even smaller. So that would be one area that's super deep tech and super hard, but one area that I would be looking into, new lithography methods, or anything, that could be compatible with that. Then, analog AI chips. And that's something I mentioned before. There's one particular approach that is sort of popular, that is memristors. So using a material whose resistivity depends on the history of what voltages you apply. And you use a large voltage to tune the resistivity to a certain value that encodes the value of a neuron, say, in a neural network. And then you apply small voltage to just do inference, and it's not altering the resistivity anymore. So you can basically encode a neural network by hardware design. And that's just one approach. You could use resistivity, capacity, any other physical principle that embodies a neural network by hardware design and makes it order of magnitudes, not just one or two, like literally 100,000 times more efficient to run AI inference. And that's not only inherently interesting because you save energy, but it might also allow you to stack your chips into the third dimension. At the moment, chips are more or less flat. Forget about gate-all-around approaches and stuff. It's basically flat. What I'm talking about is really layers, dozens, hundreds of layers on a chip. And your major issue is really heat, on how to get rid of heat from the chip. One approach might be to go analog and just be a lot more energy efficient to not produce all this heat in the first place. And that also brings me to the third point, and that is on-chip memory, which is really a constraint for AI. Like at the moment, the worst constraint is not necessarily GPUs and AI chips per se, but it's really getting data from the memory into the AI chip for processing, overcoming this von Neumann bottleneck, and having a very fast and efficient memory. So there are already approaches to new memory where you have multidimensional memory, like 2.5 layer memory, which is one step that is pursued by TSMC. But if you find a better way to do on-chip memory, even in a multidimensional way, this could be huge and potentially worth another generation company. Then we get one step higher. We've gone from lithography methods to chips to on-chip memory, and now we'll connect everything. We just had this question before about chip interconnects. I think this will be huge, really, in several ways. On the one hand, it really gives you like a high-speed link between your processor and your memory unit to overcome the von Neumann bottleneck basically by brute force, by just providing a faster way to transfer data. That is one thing. But the other thing is also it allows you to disintegrate your chips into various chiplets, into different functions. So you used to have these large monolithic systems on chips, one large chip with all the functionality. Now, the problem is yield. If one part goes defect during manufacturing, you could throw away the entire thing. Or it's just very hard to get a good yield on manufacturing. If you disintegrate this into different chiplets for processing, for memory, for different functions, then you could reuse those building blocks. But also if one of them defects, you could just swap it out. And now your challenge becomes to interconnect all of this, where really optical interconnects could come in and provide a high-speed link. So this will be huge. And then last but not least, optical computing. And I think this is really under-indexed. Like we've heard a lot about quantum computing, and everyone is super hyped about quantum, and it will be great. We just don't know when. But what we know for sure, also from an investor's perspective, within the next 10 years, optical computing will be big because the advantages are overwhelming, and the science is very clear on that. You get much more energy efficient compute, much higher bandwidths, nothing is faster than light, so you get really good latency. The main question is there more an engineering question, how to get there, because you need to integrate with slow and inefficient electronic systems, and you need to find a use case where it makes sense to integrate first, to then, go all optical. Find a very specific case in firewalls, in encryption, some other domain where you go optical, and then increasingly the entire pipeline goes optical. And in the end, in 10 years, your Mac will have an optical processing unit if Ecotonic succeeds. Those guys are also around. They do optical general purpose chips. Go talk to them. They're amazing. The future will be optical. So these are a couple of theses that I've learned about, among others, working in VC, but also writing a blog on the future of computing. If you put in future of computing, these 3 words into Google, you'll find it within the first few entries. And it's a blog that I've started as a personal side project. It's really unrelated to my main job, and then it's good PR. And I'm interviewing startup founders about their journey and their technology for almost 2 years. It's been 80+ interviews from AI to quantum to optical to neuromorphic, really learning about the journey, how they think about company building, but also putting different technologies into perspective. And by now it's become really a great resource to learn about all these different developments. So last but not least, that's me. If you'd like to connect, here's my LinkedIn. We at Luna Ventures invest pre-seed and seed up to $1 million into computer science moonshots. That's both software and hardware. So if you're working on a new revolutionary IT or hardware technology, please come talk to us.